Swayam Prabha. Digital India. Educated India.
In this lesson, we'll summarize the differential equations and responses of first order system, and also look at commonly made statements such as a DC current cannot pass through a capacitor, or you cannot have a DC voltage across an inductor, and so on. Okay. So first of all, we'll take this as an example, but the statements I make will be by and large true for every first order circuit. Okay. Any circuit with a single capacitor and any number of independent sources and other linear components can be reduced to this form. Okay, this Vs, R and C. Okay, this may be the actual circuit, or this Vs and R could be the Thevenin equivalent of whatever is connected to the capacitor. As long as you have a single capacitor, you will have a first order system at most, and this will be the equivalent circuit. Okay. Now let's identify different possible variables. I have marked Vc, the capacitor voltage, Ic, the capacitor current, and Vr, the voltage across the resistor. Now we have already seen that we can write the differential equation for this circuit in terms of any of these variables. If we write it in terms of Vc, this is the differential equation. In terms of IC, this is the differential equation, and finally in terms of VR, this is the differential equation. And these are generally true. Okay, we have not made any assumptions. These are just the differential equations we get if we choose Vc as the variable, or Ic as the variable, or Vr as the variable. Now the thing you can notice, which I have pointed out earlier, is that the left hand side is exactly the same. So in the source free circuit, when Vs is 0, all three essentially give you the same differential equation, okay, with the right hand sides being 0. Okay, if we set Vs equal to 0, that is the source free case, then the right hand side will be 0, 0 and 0. So you can see that the differential equations are exactly the same if the right hand sides are 0, only the variables are different. Now because the differential equations are the same, each of these variables follows the same response. Okay, so the natural response of each of these, which corresponds to the source free case, would be Vc would be Vc of 0 exponential minus t by Rc, and for Ic also it will be Ic of 0 exponential minus t by Rc, and finally we have Vr of time would be Vr at time 0 exponential minus t by Rc. Okay, so once you are familiar with the basics of a first order RC circuit, you don't even have to write the differential equation. You will be able to write down the natural response simply by identifying the initial condition, okay, which you can do by regular circuit analysis. Now to understand this properly, you need to understand first order differential equations and all the things we have discussed, but after you have enough experience with it, any first order system you should be able to solve simply by identifying the appropriate initial condition. And this is true for any variable in the circuit, because all variables will follow the same pattern as you can see over there. Okay. Now if Vs is assumed to be a constant, that's the case we have looked at so far. Okay, then also things are quite easy. If Vs is a constant, then again these two will be 0, because the time derivative of Vs is 0. Okay, and we know the solution to that as well. In fact, it's exactly the same solution. Okay, Ic will eventually go to 0. By the way, if you remove this derivative term, you will be left with something else, just an algebraic equation, and that is the steady state solution, right? For constant inputs, the steady states of any of these variables is also a constant, and the only way these things will be constant is if the derivatives are 0. So the steady state equation is basically when the derivatives are 0, steady states for constant inputs, and the responses are the same, only for Vc is it different. Now again, in a general first order circuit, which could be more complicated than this, first order of course means a single capacitor, but you could have any number of resistors, control sources, any number of independent sources, and so on. So you pick any variable, it will follow in general some equation like this. And what is the solution to this? The way we have written it, when Vs is constant, Vc of t is Vs plus Vc of 0 minus Vs times exponential minus t by Rc. I will elaborate on this a little bit. Let me write down the differential equation as well. The solution to this is okay, this is written in the form of the force response plus the natural response. Now it looks like this Vs is specific to this one, but if you think about it for a moment, you will realize that whatever appears here is nothing but the steady state solution. Okay, so if you have a constant input Vs, then the steady state is given by dVc being 0, which means that we take only this part of the equation, Vc equals Vs. This is what happens after steady state is reached. And like I have emphasized, every circuit that we will consider now will be a stable circuit, and this sort of steady state will be reached. The natural response will eventually die out. So this whole equation can be written in a more general way as Vc of infinity plus Vc of 0 minus Vc of infinity times exponential minus t by Rc. So Vc of infinity is the steady state value of Vc. We know that it will asymptotically reach this value, and Vc of 0 is the initial condition on Vc, and this solution is valid when Vs is a constant. That's very important. If you have Vs to be some arbitrary function of time, you can't simply substitute that function of time over here. Okay, so this is valid only if Vs is a constant. So now this is a general form of solution to any first order circuit. We have been looking at RC circuits, that too with a single R and C, but as long as you have a circuit with either a single capacitor or a single inductor, and the rest of it, the circuit could be as complicated as you can make it. Okay, you could have any number of independent sources and linear elements such as resistors and control sources. We know from Thevenin's theorem that all of that can be reduced to a single voltage source in series with a single resistor at the terminals of the capacitor, and if you have an inductor, again the same thing can be done. So the result is a first order circuit. The solution to any variable in such circuits will be of this form. Okay. The constant input part is important. Let's say at some voltage Vx, as a function of time, it will be the steady state value plus the difference between initial and the steady state values, which decays with time. Okay. So like I already pointed out, this is the steady state value, and this is the difference between initial and steady state, and this is the time constant. Okay, and this is true for any current also. In general, it will be of this form. Okay, and of course it will have the same time constant. Okay, so this is the time constant, this is the steady state value, and this part is the difference between initial and steady state values. What is the point of writing down all this? Like I mentioned earlier, if you have a first order circuit with enough experience, you should be able to write down the response even without ever writing the differential equation. Now, this is not to say that you should forget everything you know about the differential equation. So, initially you write down the differential equation and make sure that everything is consistent. But after a while, you will be able to simply identify the steady state values of either currents or voltages. I will explain how to do that in a moment, and the initial values of currents or voltages. And once you identify those things, the only thing remaining to be identified is the time constant, and that also can be identified because you have either a single capacitor or a single inductor, and the effective resistance that appears across the capacitor or the inductor in the source free circuit, that is the equivalent resistance, and the product of the resistance and capacitance is the time constant. Okay. Now, for all the cases that we know, this will be modified a little bit later. How do we do these things? So, initial condition, it means that before applying the input or before the step changes to some other value, the capacitor has some voltage, and usually you find it by assuming that the capacitor voltage does not change instantaneously. Okay, this is true if the current in the capacitor is finite. Okay, based on this you will be able to calculate the initial condition on any variable in a circuit. Okay, so again let me take a simple circuit like this, and let me say that the input Vs changes from 0 volts to 5 volts, and the voltage on the capacitor just before the step, let's say the step occurs at t equal to 0, this superscript of minus means that it is just before the step, and that is equal to 2 volts. Okay. Now, first of all, the value of the capacitor voltage, if you wanted to find the initial condition on the capacitor voltage, that is just after the step, which is indicated by 0 plus, this will be the same as Vc of 0 minus, because we cannot have infinite currents in this circuit. If there is an infinite current through the capacitor, then that infinite current also flows through the resistor, which means that there has to be an infinite voltage across the resistor. We will assume that our Vs is finite, so we cannot have infinite currents in a case like this. Later we will see circuits where that can happen, but in this circuit it cannot. So this will be equal to Vc of 0 minus, which is the same as 2 volts. Instead, if you are interested in Vr, okay, what is Vr, the initial condition on Vr just as the step is applied? Vr is nothing but Vs minus Vc. So if Vs is 5 volts just after the step is applied and Vc is 2 volts because it is continuous, Vr would be 3 volts. Okay. And finally, if IC were of interest, then you can see that this IC is nothing but the voltage across the resistor divided by R. Okay. And the initial condition on the voltage we have already found out. So the initial condition of the current is 3 volts by R, and if R is 1 kilo ohm, it is 1 milliampere. Okay. So you will be able to find out the initial condition directly from the circuit quite easily. Okay. Then the final condition or the steady state condition. With constant inputs. This is important. We are now dealing only with constant inputs. The differential equations we wrote were general and independent of what kind of input you have, but the solutions we have obtained is only for constant inputs. Now, what makes this easy to evaluate is the following. If you have constant inputs, the voltages across the capacitors will also be constant in steady state. Okay. So this fact that we have constant inputs means that capacitor voltage is a constant in steady state. Okay. So that gives us a great simplification. If the capacitor voltage is constant, the capacitor current, so here we have a constant voltage. So the capacitor current IC, which is C times the time derivative of the capacitor voltage, will be 0. Okay. So if you have constant inputs and you have reached steady state, the capacitor currents will be 0, and which means that they can be treated as open circuits. Okay. This is fine. So again, we'll take the same example as before. If you are interested in calculating the final value with a 5 volt input and a 1 kilo ohm resistor and some capacitor C, as far as the final value calculation is concerned, we saw that the capacitor current will be 0, and for the final value calculation only, we can open circuit the capacitors. Okay. And now it's very easy to see what is the final steady state voltage. It is equal to 5 volts because no current flows through this resistor either. Okay. So if they call this VC, VC of infinity is 5 volts. Okay, this is a very simple circuit, but in any circuit you can open circuit the capacitor, then you will be left with only independent sources and resistors or control sources. This is like the earlier circuit analysis without capacitors, which you can do quite easily. Okay, VC steady state value is 5 volts. On the other hand, if you wanted IC, then you can clearly see that IC is 0 here because of the open circuit. So IC of infinity is 0. And similarly, if you are interested in VR as that was the variable of interest, then you can see that VR is also 0 because there is no current through the resistor. Okay. So this also can be identified quite easily. Okay. So we discussed how you can find the initial and the final values by inspecting the circuit or by doing simpler circuit calculations. That is, you don't have to worry about the differential equation. Okay, you may have to solve for some algebraic circuit, that is a circuit with independent sources and resistors and control sources and so on. And finally, calculating the time constant is also very easy. So let's say we have any circuit with independent sources, then resistors and control sources, and we have two terminals available to us, and across these we connect a capacitor. This is the only capacitor in the circuit. Okay. In that case, this circuit will be at most of first order, and the rest of this can be represented by a voltage source VTh in series with RTh, and we have our capacitor C. Then the time constant of this is found by setting the independent sources to 0, which short circuits this voltage source, and we have this C, and you have to find the resistance across C, and that is equal to RTh. So the time constant is 1 over RTh times C. Okay. So in other words, if you have a first order circuit, every variable will follow this type of behavior. Then you first find Ix of 0. This is by assuming that capacitor voltages don't change, and this is true if the capacitor currents are not infinite. We will later see examples where it can be infinite. And you find the steady state values, that is values at infinity, by open circuiting the capacitor. If you have an inductive circuit, you find the steady state by short circuiting the inductor, because the inductor voltages are 0 in steady state with constant inputs. Then you have these values at 0 and infinity, and the time constant can of course be found by finding the Thevenin resistance across the terminals of the capacitor in the source free circuit. Okay, so the entire response can be written down by inspection.